Peshawaria.
Yes, that's
Laminate Succinct SIMD friendly verifiable FHE. For the next speaker, would you mind just acknowledging where you are so that I can see?
All right.
Okay, thank you.
I'm good to start.
Go ahead.
Okay, thanks everyone for coming. I'm really excited to talk about this work, which is a different way to try and get verifiable FHE, which has very different trade-offs as we're going to talk about. This is joint work with wonderful collaborators, Thomas Liu, Ben Fish, and Eran Tromer. So let's start with the motivation. So suppose that you wanted to outsource a sensitive computational task, in this case, analyze my DNA and recommend some preventative treatment. This is sensitive. The cloud might not respect your privacy. You might tell your insurance company that this person needs a higher premium because they have some pre-existing condition. So that's a problem. Another issue which comes up in outsourcing computation is the server might be unreliable. They might be incentivized to lie to you, in this case, telling you you need expensive medication when you don't actually. Fortunately, we have solutions to both these things in cryptography. So the first one, solving privacy, we can do with fully homomorphic encryption. And the purpose of this slide is to remind you what this is and also to get you used to the notation I'm going to use here. We have an input. We can encrypt the input. And then there's a way to do computation on encrypted data to get an encrypted output, which we can decrypt. And this symbol here means the diagram commutes, which means that however you go from input to output, you're going to get the same result. And this dashed line shows what the cloud is actually going to see. So the takeaway is the server is only going to see ciphertext. They're not going to learn anything, but they're able to compute any arithmetic circuit they want to. We can also solve integrity with snarks. Hopefully, I don't need to define a snark to this audience, but we need completeness, soundness, and very importantly, we need succinctness. The whole point of these delegation schemes is that the client should gain something. It should be easier to verify the proof than to do the computation by themselves. So the question is, how do we get both, right? How do we solve for integrity and privacy? Well, there's two approaches, right? One is to do snarg over FHE, where we prove that we did ciphertext operations correctly. That's what we just saw. Another approach is to FHE over snarg, which is where we homomorphically evaluate a plaintext proof under FHE, right? And a priori, it's not clear maybe how these two are different, so I want to take a second to explain the differences. So let's look at the snarg over FHE approach. We start with a payload circuit that we want to delegate. We can evaluate that circuit under FHE, and it's this complicated computation here, which takes a representation of a ciphertext of A, a representation of a ciphertext of B, does a bunch of operations, and then gets a representation of the product ciphertext. We take this entire trace, computation trace, which means all the messy stuff that happens going from ciphertext A and ciphertext B to a representation of ciphertext AB, and we feed that into a snark prover, which correctly proves that you did this FHE evaluation circuit correctly, right? And notably, as we just saw in the last talk, this includes approximate arithmetic, which is not easy to do. And a lot of very smart people have come up with very smart solutions to this, but this is just inherently a difficult thing to do, right? This is a hard problem. The alternative is we can do FHE over snarg. Again, we start with the same payload circuit. We evaluate it under FHE, and then we take the encrypted trace of the payload circuit and give that to the snark prover instead, which means that we don't care about the messy in-between states between gates, right? We care about the ciphertext of A, the ciphertext of B, and the ciphertext of AB. I don't care what you did in between. The snark prover doesn't care what you did in between, right? So this becomes a lot easier to do because, theoretically, we can find a good snark prover under FHE, and we're not limited by how complicated the payload computation is and whether it's doing a lot of multiplications and stuff, which are hard to arithmetize. And here are a few constructions that do this, right? And notably, this is producing an encrypted proof that A times B is equal to C. So the client who receives this proof has to decrypt it first and then verify. So let's compare these two approaches at a bird's eye view. So the snarg over FHE approach and FHE over snarg, they both have good integrity guarantees, right? If the client is convinced that this is the right output, it probably was the right output. From a privacy setting, the FHE over snarg has a slight issue. Because of this decrypt then verify phenomenon, if the server has access to a feedback channel, like in particular whether you complained about the proof being invalid, there's a 1-bit leakage, right? Which is, in practice, could be really problematic, right? So it's important to acknowledge that. Public verifiability, snarg over FHE, I'm proving that I did the ciphertext algorithm correctly. I manipulated them correctly. FHE over snarg, it's not publicly verifiable, right? First, you have to decrypt with the secret key, and then you can verify. And I put an asterisk because you can make it publicly verifiable after the fact by proving that I know an encrypted proof, but OK. And as far as server efficiency goes, both of them were really bad before our work, and client efficiency was good in the snarg over FHE case, but bad in the FHE over snarg case. And that's not inherent to FHE over snarg, it was just limitations of past constructions. As we'll see, what we do is we make the server efficiency good and the client efficiency good. And you'll see that the server efficiency here changed to decent because of batch pack and proof, the thing we just saw. Great, so what's our contribution? We give a compiler that adds integrity to any BGV or BFE-based delegation scheme. And we're not the first people to do so in the FHE over snarg world, so let's compare the bottom lines. For an arithmetic circuit with 16 billion fan-in 2 gates, here's the table of comparisons. And I want to walk you through what this means. Right. So the first solution is the trivial solution, where I evaluate the payload circuit under FHE, and then I literally send you every single part of the trace. Right. So this is clearly trivial. The proof size you get is 327 gigabytes. So that's really the benchmark to beat for your protocol to be usable at all. As we see, past works here, Blind Fractal and Phalanx, fail to beat the trivial solution. Right? Not only are their server overheads very, very large, but the proof size is also much larger than just writing down the entire trace of the circuit. So something strange happened there. And in Laminate, we can see that we get a server overhead that's somewhere in the order of 5x to 67x, just FHE without integrity. And our proof size is 13 megabytes. Okay, and this range depends on the topology of the payload circuit. So just a quick teaser about the name Laminate. It's supposed to indicate like a thin layer added on top of payload computation to ensure its integrity. So this is like the picture you should have in mind with why we named our scheme that. So, OK, what are the issues of prior work in the FHE over snarg space? Well, they missed some very important end-to-end server costs. In particular, like they hard-coded the field of the snarg, which can give you high witness reduction costs because the snarg prover now needs to do expensive non-native arithmetic, which is even worse in FHE than it is in the like plain text world. The second is that they do these like NTT-based polynomial commitments under FHE, and NTTs are very inefficient under FHE, right? Like you have an n-squared depth 1 algorithm, or you have like an n log n log operation, but log n depth algorithm. For the experts in the room, hopefully you know what I'm referring to. But it leads to very bad server overhead. And then finally, their proofs are not even succinct, right? Like the client of the previous schemes are not gaining anything from delegating. So the natural question you might ask me is like, how and why were these things missed, right? And the answer is that it stems from incorrectly accounting for SIMD, and this masks the bad asymptotics of previous schemes. And I'll hopefully, if you don't know what SIMD is, hopefully you stay tuned. I'll get to it in just a couple of minutes. So here's the talk outline. I'm going to overview our construction, and then I'll tell you about the evaluation of it and conclude and what the future directions are. Great. So our goal is to build an FHE-friendly snarg prover. Right? We want to evaluate a snarg prover under FHE. So I need to tell you what it means for something to be FHE-friendly. And most like FHE schemes, in particular BGV, BFE, the ones we're interested in, have some noise growth consideration. When you do operations on ciphertext, the noise increases. And if the noise exceeds a threshold, then you can't decrypt. So if you're evaluating complicated circuits, you need bigger ciphertext, which means slower operations. Multiplications, in particular, add a lot of noise to your ciphertexts. So our very good first approximation of what it means for a circuit to be FHE-friendly is that it's a low multiplicative depth arithmetic circuit. So today, when I say FHE-friendly, low multiplicative depth, just macro that in your head. Cool. And so what we'll do is we'll use the GKR proof system. And this is a very simple proof system which has 3 very nice properties I'd like to highlight. The first is that there's no witness reduction. The prover works directly on the computation trace. There's no extra step. And it's field agnostic, for those of you who are familiar. The second is there are no polynomial commitments to the computation trace under FHE. And this was exploited as a bug in this Rothblum et al. Attack, how to prove false statements. But for us, it's a feature and helps us be more efficient. And then the final thing is that it admits like a very conceptually simple FHE-friendly proving circuit. GKR, for those of you who are familiar, is just a bunch of sum checks. And sum check is very FHE-friendly, as we'll see. It breaks down nicely in chunks of efficient circuits that have low multiplicative depth and parallelize nicely, in a sense that we'll see. So the next few slides are inspired by Kalai's talk. I just want to give some slide credit to her. So let's quickly review what GKR is, just so we can get on the same page. Right? You have this layered arithmetic circuit. Inputs to layer I come from layer I plus 1. And we want to claim that C of the x's gives me y. So how do we do this as a first attempt? Well, I tell you that layer 0 is equal to y, and then I open up the inputs to layer 0 and say it's A and B. And you flip a coin, and you choose to spot check one of them, let's say. And then I do it again. I say the inputs to A were C and D. You check that that makes sense. You flip a coin, and you choose to spot check one of them. And you can do this all the way down until you get to a claim about the final layer, the input layer, which you, as a verifier, know. Of course, this is really, really bad and has terrible soundness error, because if I ever flip a coin and check somewhere where you didn't lie, then you can cheat me. Naturally, G, K, and R are much smarter than this, and that's not what they do. Rather than the layer claims being something about a particular wire in a layer, it's about a linear combination of the wires in that layer, or more specifically, like a low-degree extension of those wire values. So it's the same like high-level idea that we start with a claim about layer I, and then we invoke some sub-protocol D times to reduce to a claim about the subsequent layer. So it proceeds something like this. And the intuition for why this works, if you're unfamiliar, is like basically short-simple. If one of the wires in the layer is incorrect, then most places in the low-degree extension are also incorrect. So what does this layer reduction sub-protocol look like at a high level? So it's this interactive protocol based on sum check. We start with a claim about layer I, and then we use layer I plus 1 to prove the claim about layer I, and it reduces to a claim about layer I plus 1. And notably, there's this algorithm for it from CMT 12 that is quasi-linear, and it doesn't reuse work across rounds. So here's a picture to have in your mind. Right, we have layer I. We have a claim about layer I. Using the assignments to layer I plus 1, we do this sum check layer reduction subprotocol. And as you see, the next prover message only depends on the coin flips from the verifier. It doesn't depend on any saved state from the previous prover message. And this is very nice. For those of you who've seen GKR, this is like the reduction to sum check. OK, so zooming back out, how does the GKR interactive proof work? Well, we have a layered circuit, and then we invoke a layer reduction subprotocol that's interactive multiple times. And thanks to CMT12, we have this algorithm that avoids dependence between rounds. So the prover calculates the round I message without any saved state from round I minus 1 in particular. So this becomes very FHE friendly, right? As we see, when we're doing the layer reduction from layer I to layer I plus 1, we're only using the encrypted values of layer I plus 1. Yes, we're using coin flips that are verifier challenges, but those are coming in as plain texts, right? So as far as the multiplicative depth of the FHE circuit is concerned, we're happy. Cool. So this gives us an FHE-friendly interactive GKR prover. How do we make this non-interactive? Well, we know how to make interactive proofs non-interactive. We use fiat Shamir. And the quick summary of this is that instead of the verifier actually flipping a coin in an interactive way, we simulate that, and we choose a message first, and then hash that message to get a coin flip. And the soundness intuition is that you're choosing the message before you're seeing the coin flip, so everything's still OK, more or less. Right? And you wouldn't want to see the coin flips first, because that's effectively where the verifier plans to spot check you. And if you knew ahead of time where the verifier wanted to spot check you, you could make sure to be correct in those places and lie elsewhere. OK, so fiat Shamir, hopefully most of you are familiar with. So what if we just took our entire GKR prover and ran it under FHE? Well, there's a big problem, right? In particular, hash evaluation is probably not low depth. And that's not even the worst problem. Earlier, we said that the next prover message only depended on the ciphertext of the payload assignments and the verifier challenges. Well, the verifier challenges used to be plain text, so they weren't accumulating any noise. But now we've introduced this big dependency chain, and the old multiplicative depth was the max depth of computing any of the prover's messages. Now the new multiplicative depth of our FHE snarg is the sum of computing all those messages plus the sum of computing all of those hash function evaluations under FHE. So that's a big problem. This non-interactive proof under FHE is not going to be very efficient. So how do we fix this? Well, the idea is instead of doing the hash function under FHE, let's take it outside of FHE, right? In particular, choosing a ciphertext which encrypts a message still in the underlying decrypted proof is like I'm choosing the message before I'm getting the coins, right? So I can hash outside of FHE the ciphertext and get some plain text coins as a result. And this technique is credited to a bunch of people. Great, so what does that look like as a big picture? Well, our first step is the server gets an encryption of the input from the client. They evaluate this payload circuit under FHE. And then they start with a layer reduction subprotocol based on sumcheck to reduce a claim about the output layer, layer 0, to a claim about the layer 1. And then so on and so forth. We reduce a claim about the second to last layer, D-1, to a claim about layer D by running multiple rounds of sumcheck. And eventually, we send all of these black arrows to the client. And in this picture, the y-axis is supposed to represent the multiplicative depth of FHE. So our multiplicative depth overhead, as you can see from this picture, is only one level, where levels are kind of like multiplications. And yeah, this brings us to the name Laminate once again, right? Laminate stands for a thin layer of extra computation with low multiplicative depth added on top of payload computation to ensure its integrity. So in particular, if evaluating the payload under FHE took D levels, then let's call it K multiplicative levels. This only takes K plus 1 multiplicative levels to compute the payload and compute a proof. And the reason the multiplicative depth overhead is so low is because you're just doing a bunch of sum checks, right? And what is sum check? It's like the sum check prover is just computing sums of many terms. Each of those terms can be computed in low multiplicative depth, and then you can sum them up without any multiplications. So let's recall the issues of prior work. The first is that they had these mismatched fields. Well, GKR is field agnostic, and we directly use the wires from the payload circuit evaluation to prove. The second is they did these entity-based PCSs under FHE. Well, GKR does not commit to the computation trace, which allows Laminate to have an efficient server. And then finally, the proofs were not even succinct in prior work. So the discussion is coming, but first, I need to go to the next part of the talk and tell you what SIMD is. So SIMD stands for same instruction, multiple data, and it's effectively these vectorized operations. And what I want you to take away from the slide is I made the SIMD addition very, very large to show you that this vectorized element-wise operation is much slower than if you did a regular addition. Right. And so an oversimplification that we had earlier is I was pretending like a ciphertext encrypts just one scalar, but in reality, a ciphertext encrypts a vector of scalars, B elements, let's say. And FHE's gate set is not just addition and multiplication, it's actually SIMD addition, SIMD multiplication, and something called rotation, which allows you to do things in between slots. And again, these are just like element-wise addition, element-wise multiplication. And as a note, you shouldn't think of B as being a small constant. It's concretely very large, like at least 16,000, let's say. So yeah, let's talk about past work once again. They seem to claim server runtime overhead of less than 2x, which would be amazing, right? But we reported very different numbers for them. And the reason is because they use an unrealistic benchmarking model, which I want to spend a slide telling you about now. This unrealistic model is the single slot mapping, right? We have a payload computation on BN regular gates, like fan-in2, and they turn it into a payload computation on BN SIMD gates. Right, so if you have to do an addition like this, they turn it into a vectorized edition where you only care about the first element and they just ignore all the other elements, which is very wasteful. A more realistic mapping would be if you have a payload circuit on BN regular gates, you should get a FHE payload circuit with like n plus change SIMD gates. So here's an example of a payload circuit that has like 3B fan-in, 2 gates, but the SIMD circuit only has 3 gates. And the takeaway is that like payload computation should use all the slots. It's like critical that BGV and BFE, you're using all of the slots. It's crucial to having like an efficient payload computation in the first place, even without integrity. Okay, so when it comes to benchmarking, the payload computation should use all B available slots. But what past works are doing is they're considering payload computations that only use one of the slots and then use all the slots for proving, and then compare the ratio of doing both to just doing payload computation. And this is kind of like comparing the ratio. This is kind of like using 16,000 threads for proving and only one thread for computing the payload, which is not a fair comparison. On the other hand, Laminate, we are still able to do proving with the same asymptotic complexity, but our payload circuit is now B times larger because it's using all B slots. And so the takeaway is that our GKR-based proof generation is like omega of B times, where B is like 16,000 or more, faster than prior FHE snark constructions. So some payloads, of course, cannot exploit SIMD, but we have a variant of Laminate which is tailored to these special cases. And in the limit, you can imagine like an infinite number of Laminate variants that optimize for different cases, different special cases of payloads. As an aside, one advantage over the SNARG over FHE paradigm is that that paradigm can't meaningfully optimize for these special payloads that don't use all the slots. Okay. Now I want to say a little bit about proof size issue. So because of SIMD, the proof system communication pattern without FHE is I would send you maybe in GKR just a couple of field elements every single round. But the smallest unit I have now is a ciphertext. And a ciphertext encrypts B things. So what you get is something that looks like this as a very simple proof system. I wanted to send you 1 dot in every single round, but I was forced to send you B dots. So how do we fix this? Well, instead of sending you the sparse ciphertexts 1 per round, what we can do instead is we can commit to those sparse ciphertexts and then give you a packed dense ciphertext as well as a proof of packing that shows that these sparse ciphertexts were consistent with the commitments that we actually did send. And this is a lot more complicated than I'm putting it on the slide. It's very interesting. You should check it out. I don't have time to tell you about it in its full generality now. But the summary is that this transcript packing technique adds 1 multiplicative depth from plain text ciphertext multiplication, and it reduces our proof size from R ciphertexts to like R over B packed ciphertexts plus some change. Cool. So let's talk about the evaluation. Comparing Laminate to prior FHE over SNARK constructions, we have the following table. Here we benchmarked a payload computation with 1 million FHE SIMD operations that use all of the 2 to the 14 slots. As you can see, Laminate is like 2,300 times faster than Phalanx and admits proofs which are roughly 70,000 times smaller than Phalanx. But that's not the interesting thing to look at. We're more interested in how Laminate compares to the gold standard, which is honest evaluation under FHE of the payload circuit without a proof. And as you see here, we looked at various representative types of payload circuits and found that for some payload circuits, the server overhead can be as low as 5.5x. And these are payloads that fully use SIMD. If you didn't fully use SIMD, you could be much, much faster. To conclude, our contribution is we added a compiler that added integrity to BGV or BFE-based delegation. The server overhead can be as low as 5.5x for payloads using the full SIMD width. And we did this by using the GKR proof system that doesn't have to commit to the encrypted trace. Importantly, Laminate is very conceptually simple, which I want to underscore is very, very important in especially with all the bugs in proof systems these days. It uses a field-agnostic proof system, so there's no field mismatch. There's no witness reduction. Transcript packing is a cool technique which can really reduce the proof size and client runtime. And then some limitations which were discussed also in the previous presentation it's inherently designated verifier. You have to decrypt first before you can verify the proof. We don't yet support private server inputs, coming soon, hopefully. And it fundamentally cannot support CKKS right now because we don't have good snargs for approximate computation. Finding an FHE-friendly snarg for approximate computation is just another constraint. More optimizations and a full implementation is also pending. If ever anybody is interested in working on this, I'd be happy to chat offline. There's a QR code and link to our ePrint. Thanks so much for listening.
Thank you, Kabir. We have time for one or two questions. So I was just curious because I think you do mention in your paper about like the issue about lack of public verifiability and the one-bit leakage.
The one-bit leakage, yeah.
And that is, like, you still don't know how to handle that in an efficient manner. How if you were to add that, compose it with something else to get public verifiability, how bad it would be?
Some past works, like the Gamma et al. Paper, showed the blind ZK snarks paper, showed that the client who gets the encrypted proof can efficiently generate like a proof that I know an encrypted proof that this ciphertext underwent this transformation and got to this ciphertext. That's efficient as far as they claim. I haven't looked at it. The one-bit leakage problem, I think, is just inherent. I'm not sure what to do there. Yeah, like, of course, I think snarg over FHE would be the gold standard, but that's hard. So we look at this relaxation in some sense.
Makes sense. All right. Well, thank you for your presentation.
Thank you so much.
All right. So I'm actually Bharat. Oh, so you already. Thank you for getting all set up. So the next talk is by Bharat Nambut.